Hey everybody, here's a quick video lesson on the relationship between Gibbs free energy and the equilibrium constant. Now in order to be able to relate delta G and the equilibrium constant, we need to once again assume standard state conditions. And in class we talked about standard state conditions being 1 atmosphere of pressure and 298 Kelvin. But there's also a standard state condition for concentration. And if it's dealing with solutions, they are all 1 molarity in concentration. So all solutions are 1 molar, and that is standard state conditions. This will show up more when we start talking about electrochemistry in the next chapter, but I was thinking of adding it now just so that it's on your radar. So to make this easy, if delta G is negative, K is going to be very, very large, and we talked about this a little bit in a previous class in a previous video lesson. If delta G is positive, then K is very, very small. And as a review, whenever delta G is negative, we say that this is thermodynamically favored. In other words, a negative delta G is thermodynamically favorable, or a K value that's very, very large is thermodynamically favorable in the forward reaction. But how do we quantify this? Well, the College Board has given us a nice, neat formula where you just plug and chug. And if you know delta G, you can solve for K, and if you know K, you can solve for delta G. Here's the formula. As we know, delta G is either expressed in kilojoules or kilojoules per mole. Now R is a gas constant, and it's not the same ideal gas constant that we use for the gas laws, but the units are a little bit different. Take a close look. It's 8.314 joules per mole times Kelvin. T is the temperature, which at standard conditions is 298, and then the natural log of K. So if you know K, you can solve for delta G. Now you should also be able to work this in reverse. That is, if you know delta G, you should be able to calculate K. And the formula to solve for K is e to the negative delta G over RT power. So you would take delta G divided by R times T, then switch the sign, and then take e to that power, and you would get K. So let's put it into practice. Solve for K if we know that the delta G for the Haber process is negative 33.3 kilojoules per mole. Now remember, the R value is 8.314 joules per mole times Kelvin. So when we take delta G and manipulate it in this problem, we can't take it in kilojoules, so instead we have to calculate this number into joules. So I'm going to move the decimal point 3 times to the right, and we have negative 33,300 joules. And then, of course, at standard conditions, the temperature is 298 Kelvin. So let's solve for K. It's e to the negative delta G over RT power. So negative 33,300 joules over R, which is 8.314 joules per mole times Kelvin. And that needs to multiply together into the denominator of 298 Kelvin. And then all of that is, so I used my calculator and I found that the exponent is negative 13.44. And so then I took the inverse of natural log and negative second answer, and I get a number that's really, really large. And you'd expect that since delta G, remember, is negative, then K should be really, really large. In this case, K is equal to 6.87 times 10 to the 5th power. And that's how you solve K if you know delta G. Don't forget to convert your kilojoules to joules so that the units in the formula cancel each other out. Joules cancels joules, K cancels K, and this should be joules per mole, so the moles cancel moles. Remember, K should have no units whatsoever, and so all of the units in the exponent, in this case, will cancel one another out because K is a unitless value that just expresses if a reaction is products favored or reactants favored. And this one is much, much larger than 1. So as we'd expect, a negative delta G equals a products favored reaction. Well, that takes care of this little video lesson. Thanks for watching.